Greetings everyone, and welcome back to the computer screen. Well, what I want to do is take some more distortion measurements at 8 ohms using the LM1875 and TDA2050, kind of a continue on. I'm kind of curious so what I will see there, and I even retake the 4 ohm measurements. I don't think those will change, but there's some things I want to explain here with this ARTA software. Now, this software, of course, it has a spectrum analyzer mode. It's free to use. You can download it, just Google it up. And it's a paid software, but you can use it in its demo mode. The only difference is you can't save data, and that's fine. I just want to see it on the screen. So you have to set some things up. I want to make sure the sound card's set up for float, 32-bit float. I'm not sure if the chip actually supports that. I would think it would. I know some say they do, but they actually don't. That's the amplitude data. You need a lot of bits. You know, if it was only 8-bit, I could only see down to around, not even down to this level, but you know, we're seeing way down here. Noise floor. I'll explain that as well. But anyhow, you can only use one channel at a time, so we're using the right channel. This frequency here is the sampling rate, and it's set for 4800 right now, and I'll explain that, the differences, why I'm using this right now. And this is the amount of data in the FFT window. You see, well, my music player turned off and I'm getting noise. Let me turn it back on, because the output goes high impedance and it just lets noise in. So I turn that on and it goes away. But anyhow, if I select a smaller value, there's less points of data here. So it works a lot faster, but you don't get as detailed data. So this is kind of mid-range. See, it's changing slower, but when I use as many points as I can, it's a real slow update, but you get a real, you know, fine amount of data. And this Kaiser or Kaiser 5, however that's pronounced, that's the mathematics that calculate how this data is going to look on the screen here. Yeah, it's kind of the non-technical description of that, but I'm not going to get into that in this video. Okay, as far as the graph's concerned here, now this is set up in decibels. It's kind of a logarithmic function here. So what you're looking at the top would be your 0 decibel, or the maximum signal level. And you can think of that as 100%. And each step down here, every 20 decibels is an order of magnitude. So we start at 100%, so at minus 20 it's 10%, minus 40 it's 1%, then it's 0.1, 0.01, 0.001, and 0.0001. And what you're seeing here is the noise floor. I just have the music player just sitting idle. Even if I unplug the cord from my computer at the rear of the computer so no extraneous noise gets in, it really doesn't change. It's still down about 120. It might drop ever so slightly, but this is extremely low noise floor. And my music player went to sleep again. So it's picking up the 60 hertz hum and all the harmonics. That's why you see that. And of course, on this scale, it's just set up to view the audio range 20 to 20,000 hertz. Okay, so what you're looking at now is the output of my music player. It's plugged directly into the computer, no preamps or anything. I'm just looking at the baseline here. And now you can see the fundamental signal that goes almost all the way up to 0. I want to get as much data in, so I have the signal as high as I can set it. See, if I turn it up, let it refresh here, see it's clipping, so I got to turn it down one step on the volume control so I get a clean signal. Update here. Okay, fundamental, and you see the little harmonic distortion peaks. And these two, the second order and this third order, just go above minus 100 a little bit. So those are what is the major contribution to its distortion reading right here. And you can see why I like to use the music player. It's extremely low, 0.0035%. Now this distortion plus noise, that's looking at the entire spectrum. Total harmonic distortion just looks at the harmonic areas. You know, when the fundamental is 1000, so second order would be 2000, the third would be 3000, 4000, 5000, so on and so forth. But plus noise looks at the entire spectrum and adds it in. And this is pretty much as low as I can get. It's a function of the sound card and probably the music player. You know, I don't know exactly what's causing this distortion. You know, some of it could be the music player, or all of it, and some of it could be the sound card. You know, it's analog inputs or other circuitry. Because even if I turn this music player signal level down some, so I turned it down, let it update here, and you know, this peak's dropped. Of course this peak dropped, but these are going to drop relative to that one, so you know, it really doesn't change the distortion much. Now when I was measuring the chips in the last video, I had my bit rate set to here. And well, you can still see those peaks. But see, these numbers are not as low. So I want to go back and measure that. However, I don't think it's going to make a lot of difference. I mean, the chips measured higher than this value. But, you know, especially the noise here, it's a lot higher. I really shouldn't use this one because of the limits. It'd be nice if I could get something that could go a bit lower. But the problem is, when I use this sampling rate, I'm actually measuring well beyond the audio spectrum, out to around 90 kilohertz or so. And there might be some noise we're not seeing. So you get higher values here. So that's one reason. Another thing is, now if I use 44.1, I get these bogies. See these bogies? They're not harmonically related. Now let me pick this one here and show you. Come on, there it is. Now I gotta move this cursor to measure that peak. It's a little tedious to use. Probably have too many data points set up on the screen. It takes forever. So I gotta find the lowest number here, which means the highest point. There it is. 92. Wait for this thing to reset. Okay. 87. Okay, it's starting to go up again, or down, I guess you could say. Oh, I just hit the wrong button. 87. You see it's at about 14,600. That's non-harmonically related. That's something to do with, I don't know, aliasing or digital capture of the signal. But when I use 4800, all this crap will be gone. See? Clean. So using 4800, I don't get any of that those bogey data points there, those bogey peaks. Okay, so what I've done now is plug in the preamp into the circuit. So now it goes music player, preamp, and then into the computer. And you can still see the spikes. They're a little bit higher now. And it's measuring 0.00. Well, it's jumping around 4 something. If you remember before, it was 0.003 something. And the THD plus N, it's not much difference. It was like 0.016. So we're adding additional amplification into the circuit. You know, I reset it so that the amplitude's the same, but when you do that, you're going to see different values showing up here. So we're getting a very, very small amount of additional distortion in the circuit. Okay, so this will be our baseline. We'll just say 0.005%. I probably won't pay much attention to this THD plus N value. The reason you see it jump like that is because the signal on the music player is 30 seconds long, and it's set to repeat. And when it repeats, there's a little glitch, and it makes it pop up like that. But anyhow, we got a baseline. Let's go take some measurements. Okay, we're testing the LM1875 at 4 ohms again. See what the difference is, if any. I don't expect really any difference. Yeah, not the same. It's fundamental, and these are all of the harmonic nodes. They're very low except for these first 3 here, which are around -80. This one's up higher, not quite to -60. So yeah, same as expected. Okay, so now I have the LM1875 with an 8 ohm load, and look how the distortion has dropped significantly. It's down to 0.038. And yeah, that's pretty typical of a solid state amplifier. You'll have less distortion with less current, because dropping to 8 ohms with the same signal level cuts the current in half. So the amplifier will produce less distortion there. Okay, I RTFM'd. I read the fine manual and figured out how to get the intermodulation distortion to display on this thing. So with the LM1875 8 ohm load, I'm getting an IMD of 0.043%. So yeah, that's not too bad. With the 4 ohm load, it was 0.078, so it's pretty close to the just the regular total harmonic distortion figures. So what I'll do now is get the measurements off the TDA2050, and I'll come back with the results. I have to show you this here right off the screen. This is the TDA2050 at 8 ohms. I'm doing the 1 kilohertz measurement there. Look at that, 0.006 something. Jumps around. Now that is low distortion. That is excellent. Just for grins and giggles, I hooked up the JAT501 amplifier. It's running at 4 ohms now. And check this out. This is at the baseline signal, or I'm sorry, baseline distortion. You know, pretty much 0.005. And remember, this node was in the original preamp node, so that amplifier is not adding any sort of distortion that I can measure. I cannot go low enough with the 501 amplifier to measure its distortion. I am using the same signal level that I measured the other amps at. I have to measure it at higher and lower, to get a full picture of its distortion performance. However, that is beautiful. Okay, let's talk about the results here. So again, our baseline for measurement here, by plugging the preamp directly into the computer and getting its measurements at 1 kilohertz is 0.005%. And with the 18 plus 19 kilohertz intermodulation test, it was also 0.005%. Now, due to the attenuator I'm using, all the tests were measured at the same RMS output voltage of 8.2 volts. And that's the maximum signal into the computer before the internal sound system starts to clip. You want to get as much data into the computer by using as much bits so you can get most accurate reading. Okay, we'll start off with the LM1875. Again, with the Four Ohms, we got 0.072% distortion at 1 kilohertz. Intermodulation test was quite similar, and that's pretty good, 0.078. 8 ohms, not really unexpected, the distortion is lower because less current, 0.038, and with the intermodulation test, 0.043. For this type of chip amp, this is about what I would expect. If you think about it, it's still less than 0.1%. And that's just what my personal reference point for considering something hi-fi is. Well, things are still interesting here. The TDA2050 is still much better. We get a little bit lower because when I was measuring the signal before, like I said, I was using that really high sample rate and was getting that extra noise that was kicking up these numbers a bit. So now we have a much lower floor at 0.005%. At 4 ohms, I actually was able to get a little bit less. I think it was 0.026 or something like that before. Intermodulation test is also pretty good at 0.031. But look at this, 8 ohms, 0.006. Wow. Intermodulation test is also pretty low at 0.012. Now, I wouldn't put much faith in this number because it's so close to our baseline. It's likely this would go even lower. So, wow, pretty impressive from the TDA2050. Like I said in the last video, I would expect the LM1875 to do better than this one, but this chip really surprised me. Though, yeah, it still had some issues, like it needs help with stability using the teal network on the output, where the LM1875 was better in that regard. And the circuit design they used, you might give up something to gain something. That's just the way it works out. Last but not least is the JT501 project amplifier. And yeah, we got some pretty interesting numbers here as well. Now this is right down at the baseline, so it's not adding any distortion. And it's the same at the 8 ohm measurements. So they're the same because it's down at the baseline. It's not adding any measurable distortion. This is just the limits of my ability to measure. This amp is amazing, really. It's probably down at 0.001 or below, especially that it's not changing with the 8 ohm load, because the distortion would be much lower with the 8 ohm load. The intermodulation test, it's 0.009, but what's interesting with 8 ohms, it was slightly higher. I mean, it's one click higher. It's so close to the baseline that I can't put much faith in that measurement. And because it's so close, that's probably why it's just the error of measurement. But yeah, really impressed with this project amplifier. It's stable. It just doesn't have any issues with it. Low distortion. I'm just so glad and thankful the amplifier turned out as good as it did. So I'm glad to be able to get these measurements, but I really need better equipment. I have my eye on a product called the Quantasylum Distortion Analyzer, a company called Quantasylum. They make various test products. And because it uses a computer, it doesn't have its own screen or anything. It's a little bit less. You're taking some of that cost out by interfacing it with the computer. And after shipping and taxes and everything, it's probably a little over $500. Couple quick questions. Somebody was asking, or a couple people were asking, where did I get my LM1875? Well, the first test I ran in the other video was the one that came with the kit. You know, they come out of China. However, when I decapped one of those kits, the die size is exactly the same as an authentic LM1875. And when I swapped in another LM1875, which I purchased from DigiKey, I'm seeing the exact same distortion nodes. You know, when you look at the spectra and you see everything's the same, that's a pretty telltale sign you're dealing with the same chip. So those kits, at least when I bought them, you know, anything can change. But when I bought them, those are authentic LM1875 chips. I guess they're supposed to be pulled out of products that didn't make it to sale or something and are resold in these kits. Again, if you buy it now, I can't guarantee they're authentic or not because they could change things. But yeah, if you like the LM1875, I mean, it's still under 0.1. It's still a very good amplifier. It's got good numbers. It's just that the TDA2050 is doing so well. Well, that'll wrap it up for this test. Thanks for watching.